Critics, in the previous lecture, we have studied gamma functions, its properties, and we have solved some examples of gamma functions. In this next lecture, we are going to learn beta functions. As we have seen, the application of gamma function is to solve the integration, the same is with beta functions, that we can solve the integrals using beta function. So let's start with today's topic, beta functions. With definition, beta function is defined for two positive numbers, say m and n. So m comma n greater than 0, then beta function of these two numbers is given by beta of mn equal to integration 0 to 1 x raised to m minus 1 into 1 minus x raised to n minus 1 dx. If we compare this with the definition of gamma function, the difference is in gamma function the limits were 0 to infinity, whereas here the limits are 0 to 1. Also, in gamma function there is term of exponential. Here instead of that it has 1 minus x to the power. So beta function of m and n is given by integration 0 to 1 x raised to m minus 1 into 1 minus x raised to n minus 1 dx. So suppose we consider the integration 0 to 1 x cube into 1 minus x to the power 4. So clearly x cube can be written as x raised to 4 minus 1 and 1 minus x raised to 4 can be written as 1 minus x raised to 5 minus 1. Hence, by the definition of beta function, this is given by beta of 4, 5. Later on, with the help of property, we can evaluate what is beta of 4, 5. So, now the properties of beta functions. The first property, beta of mn, is equal to beta of nm. Now, if you look at the definition, beta of mn is given by integration 0 to 1 x to the power m minus 1 into 1 minus x to the power n minus 1. And if we consider beta of nm, then it is given by integration 0 to 1 x to the power n minus 1 into 1 minus x to the power m minus 1. Now, it is easy to prove this property if we start with beta of mn, that is equal to integration 0 to 1 x to the power 1 minus m minus 1 into 1 minus x raised to n minus 1 dx. So if we replace x equal to 1 minus t, then this integration is equal to, or 1 minus x is equal to t. Therefore, if we differentiate, we get minus dx is equal to dt, that is dx is equal to minus dt. If we talk about the limits, x is from 0 to 1 as 1 minus x is equal to t. Therefore, the limits of t are from, if we put x equal to 0, so 1 minus 0, that is 1, and if we put 1, then 1 minus 1, 0. So limits of t from 1 to 0. So if we replace this value, beta of mn equal to integration 1 to 0, x is 1 minus t to the power m minus 1 into 1 minus x will be t. So t to the power n minus 1 into minus dt. And again applying by the rule of 12th standard that integration के लिमिट अगर हम चेंज करते हैं तो इंटीग्रेशन चेंजेस बाय साइन ओनली. So we get integration 0 to 1 t to the power m minus 1, sorry, t to the power n minus 1 into 1 minus t to the power m minus 1 dt, and this is nothing but beta of mn. Hence, beta of mn is same as beta of nm. Now, if you look at again the definition, integration 0 to 1 x to the power m minus 1, 1 minus x to the power n minus 1 gives us beta of mn. So what will give integration 0 to 1 x to the power m into 1 minus x to the power n? This is nothing but beta of m plus 1 n plus 1. So usually this will be helpful for us to solve while solving the examples of beta function. Like if you want to find integration 0 to 1 x cube into 1 minus x to the power of 4, and by this rule we directly get it as beta of 4, 5. Now next is beta of mn is expressed in terms of trigonometric as beta of mn equal to 2 times integration 0 to pi by 2 sine to the power 2m minus 1 theta cos to the power 2n minus 1 theta into d theta. So here if we replace, suppose we start with beta of mn, and in this definition we replace x by cos square theta. So what we will get, x by sine square theta. Therefore dx is equal to 2 sine theta cos theta, right? So 2 sine theta cos theta, and 1 minus x is nothing but 1 minus sine square theta, that is cos square theta. So replacing these values we will get the required proof. So if you look at the table of limit, x is from 0 to 1. So if you consider the table for theta, if you consider x equal to 0, then sine inverse of 0 is 0. So lower limit is 0. For x equal to 1, sine inverse of 1 is pi by 2. So upper limit is pi by 2. So if we replace this value in the integration, we get integration 0 to pi by 2 sine raised to 2m minus 2 into cos raised to 2n minus 2 into 2 sine theta cos theta d theta. Taking 2 common outside the integration and simplifying the terms of sine and cos, we get 2 times integration 0 to pi by 2 sine raised to 2m minus 1 theta into cos raised to 2n minus 1 theta. So suppose in this proof, if we replace 2m minus 1 as p and 2n minus 1 as q, so what is the value of m? As p equal to 2m minus 1, so m equal to p plus 1 by 2, and similarly n equal to q plus 1 by 2. So if we replace this value, we get very important rule, integration 0 to pi by 2 sine raised to p theta cos raised to q theta d theta, that is equal to 1 by 2 beta of p plus 1 by 2 comma q plus 1 by 2. Now while learning reduction formulae, I told you that this integration 0 to pi by 2 sine raised to m theta cos raised to n theta you can solve using beta and gamma functions also, and this relation exactly gives you the same, that integration 0 to pi by 2 sine raised to p theta cos raised to q theta equal to half beta of p plus 1 by 2 q plus 1 by 2. We require this rigorously, and recently we require this for solving the examples. Hence this formula can also be replaceable to the formula of reduction formula. Next property is beta of mn equal to integration 0 to infinity x to the power m minus 1 upon 1 plus x to the power n plus n dx. Now this property we will prove in one of the example in beta functions. So currently I will not give you the proof. So beta of mn, here if you look at the limits, ओरिजिनल डेफिनेशन में लिमिट 0 to 1 है, यहाँ पर लिमिट चेंज हुए हैं फ्रॉम 0 to 1 as to 0 to infinity, and the terms changes in this format. So we will prove this property in one of the example. And the last, fifth property, it is actually the relation between beta and gamma functions, that beta of mn equal to gamma m gamma n divided by gamma of m plus n. So if we want to find say beta of 4 comma 5, by this property beta of 4 comma 5 equal to gamma 4 into gamma 5 upon gamma 9, and gamma 4 is 3 factorial, gamma 5 is 4 factorial divided by gamma 9 is 8 factorial. So the answer of beta of 4 5 is 3 factorial into 4 factorial divided by 8 factorial. simplification will give you the final answer for beta of 4, 5. Now, in the gamma function, we have studied one property, that gamma half equal to root pi. Here, we will prove this property, gamma half equal to root pi. As the relation between beta and gamma function suggests that beta of mn equal to gamma m n upon gamma m plus n, and integration 0 to pi by 2 sin raised to p theta cos raised to q theta d theta equal to 1 by 2 beta of p plus 1 by 2 upon beta of p plus 1 by 2 q plus 1 by 2. In this expression, suppose we put p equal to 0, q equal to 0. So what happens at the left hand side? Left hand side reduces to integration 0 to pi by 2. Sin raised to 0 is 1. Cos to the power 0 is 1. So only in LHS we get integration 0 to pi by 2 d theta. And RHS changes to 1 by 2 beta of 1 by 2 comma 1 by 2. But as by the relation, this will give you integration 0 to pi by 2 d theta equal to 1 by 2 gamma half into gamma half divided by gamma 1. If you solve the left hand side integration, the integration will give you theta from 0 to pi by 2, that is nothing but pi by 2, and in the right hand side we get half gamma half square. So 1 by 2 get cancelled, so we get gamma half square equal to pi. Taking root on both sides, we get the required proof, that is gamma half equal to root pi. I hope you get this proof easily with the help of the relation between beta and gamma functions, as well as the relation of 0 to pi by 2 sin raised to p theta cos raised to q theta d theta equal to half beta of p plus 1 by 2 q plus 1 by 2. Let us solve some examples on beta functions. First example, express integration 0 to 1 x to the power m into 1 minus x to the power n raised to p dx in the form of beta function. In the form of gamma functions. So, if we compare this integration with either gamma function or beta function, you can easily guess that this is the problem of beta function, because limits are from 0 to 1, x to the power m is given, 1 minus x to the power of p is given. But this is not the problem of beta directly, because if you consider the 1 minus x to the power n, it is not 1 minus x only, it is 1 minus x to the power n. Hence, this problem can reduce to beta by substituting x to the power n equal to t. So we will replace or put x to the power n equal to t. Therefore, x is equal to t to the power 1 by n. Differentiating, we get dx is equal to 1 upon n t to the power 1 by n minus 1 dt. Look at the table of limit. X is from 0 to 1. If you put x equal to 0, we get t is 0, x equal to 1, t is 1. So limits are not changing. Hence, the integration 0 to 1 x to the power m into 1 minus x to the power n raised to p dx is equal to integration 0 to 1 t raised to m upon n into 1 minus t to the power p into 1 by n t to the power 1 by n minus 1. So taking 1 by n common outside the integration, so integration reduces to 1 by n, integration 0 to 1 t to the power m plus 1 upon n minus 1 into 1 minus t to the power p dt. If you compare this with the definition of beta function, this is nothing but beta of m plus 1 upon n p plus 1, and using the relation we get 1 by n gamma of m plus 1 upon n into gamma of p plus 1 divided by gamma of m plus 1 upon n plus p plus 1. As there is nothing simplification, this is the required solution. Thank you very much. We will continue the examples of beta function in the